a part of just 11 people. Only 11 people, right? Not 1,000 people, just 11 people you're a part of this. So only one person has the disease and the rest people have been falsely identified. So now in this case, your chances of actually having it becomes 1 divided by 11. And this comes out to be again 9%. So this is how this mathematics is connected with the common sense and the Bayes theorem. Earlier, you were thinking a part of the 1,000 people, but no, actually, you are just a part of this 11 people only, and you can find out the probability of actually suffering from the disease it's quite low. It's not 99%, it's just 9%, right? So what, when Bayes came up with this theorem, he didn't actually think that it is going to be revolutionary, but it is now. And he didn't even think that it was worthy of publication. I'm telling you something, that's the story of Bayes, how he took this Bayes theorem. And he actually was not knowing that this work is worthy of publication. And he didn't even submit this work to the Royal Society of which he was a member. And in fact, it was discovered in his papers after he died, and he had abandoned it for more than a decade. Then his relatives asked his friend, Richard Price, to dig through his papers, what work he has been doing, and see if there is anything worth publishing. And then what happens was, then the Price discovered what we know is the origin of the Bayes theorem. So Bayes originally considered a thought experiment, how he came up with this idea. So what he did is he was actually, he just did one small experiment with his assistant. He was sitting with his back to a flat table, and then he asked his assistant to throw a ball onto the table. There was a table, he was sitting, and he asked his assistant to just throw a ball on the table, right? Now this ball could obviously land anywhere on the table, and he wanted to actually figure it out that where it was. So he asked his assistant to just throw another ball, and then tell him if it landed to the left, to the right, in front, or behind of the first wall. So this is, let us suppose, the position of the first wall. And then the assistant second time also threw the ball, and it would be landed somewhere else. So then he was asking, just keep noting this down, the readings, that what is the position of the second ball with respect to the first ball, then third ball, the position of this third ball with respect to the first ball. So actually he was doing nothing. He was actually experimenting. He was just making his confidence more to find out the actual position of the first ball with many experiments, right? He was just repeating the same thing. He was experimenting, and he wanted to come up with the exact guess that where is the first ball. So when he realized that through this method, he could keep updating his idea of where the first ball was. Now, of course, he would never be completely certain, but with each new piece of evidence, he was getting the evidence that he would get more and more accurate. And that's how Bayes saw the world. And it wasn't that, he thought that the world is not determined. It's not a reality because it's just based upon the guesswork. But what we can do is we can just update our understanding as more and more evidence became available. So this is what your machine learning is doing. It's just keep on updating its knowledge with each evidence it collects, whatever information it learns. So there is another thought process we can talk about. So Richard Price, he introduced Bayes' theorem after this Thomas Bayes died, but his name was being used in his theorem only. And he introduced Bayes' theorem, and he made an analogy to a man which is coming out of a cave. And let us suppose that man has been there in the cave for a long time, his entire life. He was there only, and he saw the sun rise for the first time. And what he thought himself, what he thought to himself, uh, is this a one-off? Is this a quirk, or does the sun always do this? So then every day after that, as the sun rose again, he could get a little bit more confident that that was the way it works. So Bayes' theorem, it's really not a formula which is intended to be used just once, but it was intended to be used multiple times, and each time you gain some new evidence and you update your probability that something is true. So if I just go back to the example that we were talking about the disease. So if you, when you tested positive for a disease, so what would happen if you go to another doctor? You will get some second opinion, right? And that doctor would also ask you to go for some other test again, maybe from a different lab. So now, just to be sure that whether those tests are independent, and so let's say that the test also comes out to be positive the second time also. So now if I ask you that what is the probability that you actually have the disease? So here you can use the Bayes formula. And in the same Bayes formula that we used earlier, so what is changed now? This formula is going to be used, but for the first time, we were having nothing prior, no prior information was available to us. But now this time, once we have gone through one doctor and we have got one result, so this P of H, the prior information is available. You went to the first doctor and you got to know that my chances of suffering from the disease is 9%. So here, my prior for the second test, this comes out to be 9%, right? So now if I substitute the values here in the same formula for the second time when I'm going to the doctor, so there's the same thing. I'll just let me just write again so that you people just remember, because we learn the things when we see something that retains in our mind, right? So I'm writing it again so that it stays with you even after the lecture, and you remember this formula of the Bayes theorem, because this is a tricky formula, right? So here, all these values are the same. It's 0.99% as it was earlier. Only this important thing is this, how to find out the prior of something. So here we have the prior when we are doing it for the second time. So it was 9%. 9% means 0.09. So these values are, we are going to just substitute the values. I told you how to calculate this negation. It is 1 minus this value. So this comes out to be 0.91 into, how to calculate this? It is the 1 minus this value, 1 minus 0.99. So this comes out to be 0.01. So when you substitute all these values, it comes out to be 91%. Oh, so now you have got this, that the new probability based upon the two positive tests, it is 91%. So there is 91% chances that you are actually having the disease. So which makes sense. Two positive results by different labs, they are unlikely to be just a chance. But you will notice that the probability is still not as high as the accuracy, because the accuracy of the test was 99%, right? I told you in the very beginning that the accuracy of the test is 99%, but your chances of actually suffering from the disease comes out to be 91%. 1%, right? So this is a brief idea about Bayes theorem. So this Bayes theorem is actually being used in a number of real-time applications. I'll discuss later on in the end of the session. So just to get more clarity about this Bayesian inference, let's just talk about one more example. So let's imagine that you are at the movies. You go to the movie theater and someone drops a ticket and you pick it up. And then you can just see the person from behind only, as you can just see in this picture. You're not able to see the face of this person who has dropped the ticket, but you are just, you can just see that person from the behind with the long hair, and you just got to know that the person who dropped the ticket has long hair. This is the information that you have, but you don't know whether it's a man or it's a woman. So you have to make a guess. Based upon what you know about the persons who are at the movie theater, you can say, excuse me, ma'am, because mostly, you know, the women have long hair, but it's not so. Even the man can have long hair. So what generally you say most of the time, the more probability is that you will say, excuse me, ma'am, is this your ticket? And now imagine that this person whom you say, excuse me, ma'am, if you just see the line for the men's restroom, then you just saw that person again, right? That person is standing in the line um, for the men's restroom line, and just excuse me for a minute. There is an important call. Let me just attend. Okay, yes. So now you know, just see that person standing in the line for the men's restroom, and you know that this information, now you will make a different guess, of course, right? So Bayesian inference is actually a way to capture this common sense knowledge about the situation and help you to make some better guesses. And if I put this information into numbers, then just putting this information into numbers, let us suppose that at the movie theater, let's just assume that there are 100 women at the movies, and 50 have short hair and 50 have long hair. And there are 100 men at the movies, and 96 have short hair and 4 have long hair. Please just note down these numbers somewhere, because we are going to elaborate on these numbers for the entire example. Otherwise, you can just tend to skip the idea. So just remember those numbers. So we are assuming that there are 100 women in the movie theater, and 50 have long hair and 50 have short hair. And if we talk about the men at the movie theater, then there are 100 men, and 96 have short hair and 4 have long hair, because you know, Bayes is nothing but you are calculating the probabilities of something, right? So now in this case, we can see that there are definitely more women with the long hair. The information that you have is that someone whom you handed over the ticket, that person had long hair, but you don't know. You want to find out that whether that was a man or that was a woman. This is what you are calculating. What is the probability that the person who had the long hair is a man or a woman? This is what you are actually calculating using the Bayes theorem, right? But it's not straightforward. It involves a number of steps. So we are looking all these steps one by one through this particular example. So now you can just imagine, just see from here that here the number of persons with the long hair are more, and they are women. And the people with the long hair are, and they are man, they're very less, right? They're just 4. So what you will say, that you will assume that the person is a woman. And if I talk about the other situation, when you saw that same person in the line of the men's restroom, you saw that same person. So here the situation is different. So now there are 2 women. Let us suppose there are just 2 women from the 100 people who were standing in the line for the men's restroom. The 2 women are also standing over there, right? Maybe, and the 98 men are there. And maybe the 2 women, we can assume that they are just standing with their husband, and they're just talking with their husbands, and that's why they are in the line. And there are 98 men and there are 2 women, right? And one is having short hair and one has having long hair. So it's still half and half, long and short hair. But now there are, if you just see, if we talk about the men, there are 4 times as many men with the long hair this time than the woman, because this remains the same. 94 people are having, they are man, they have short hair, and only 4 people had long hair and they are man. And now if you just compare, then here this number is more. It's 4 times. It's 4 times men are having the long hair than the women with the long hair in this group. So now what you would say, now your answer would be different, because whatever value is more, you would go with that value, right? So now you would say that overall your assumption will change. You will say that this person is a man. Now let's take it some other way also. And here, let us suppose that out of the 100 people at the movies, overall will make one assumption that 50 of them are women and 50 of them are men. And now the different categories are broken down like this. We can say that 25 women have short hair equal, and 25 women have short long hair, and total women are 50. And if we talk about the men, then 48 have short hair and 2 men have long hair. Right. This is the situation when we are just talking about the people at the movie theater. If we talk about the people in the category for the line for the men's restroom, and then they break down a little differently. So here, out of the total 100 men, there are 98 men, right? And 2 are women. And out of that, 98, 94 have short hair and 4 men have long hair. And there are 2 women. One is having the short hair, another is having the long hair. If I just translate this to maths, then the probability that a person is a woman. So what is the probability? How to calculate the probability that the person is a woman? So it is always calculated as the total number of women divided by the total number of people. So this comes out to be 50. I told you earlier, right? 50 are the women out of the total 100 people. So I'm calculating what is the probability of women. It is 50, the number of women divided by the total number of persons. So this comes out to be 50%. And if I calculate the probability for man moving to the this, it again comes out to be 50. If I talk about the other scenario that we are considering for the men's restroom, now what is the probability that someone is a woman? So number of women are 2 in case of men's restroom. Out of the total people are 100. So it's 2% is the probability. And the probability of man, the total number of men, they are 98. So it comes out to be 98. So now Bayes' theorem is it's a little bit tricky. So we have to talk about some probabilities. So we'll talk about 3 probability concepts, and this will lay down the foundation for presenting Bayes' theorem. So the first one is conditional probability, right? So how to calculate this? Conditional probability means we want to calculate the probability of something and some condition is given to you, right? So this is conditional probability. So if I know that a person is a woman and that's the condition, then what is the probability that the person has long hair? So this is what we are actually want to calculate. That I know that a person is a woman, then I want to find out that what is the probability that the person has the long hair. So it is written as the probability, it is written as the probability of long hair, and given, I told you it is to be read as given that the person is a woman. So to get this, we just divide the number of women with the long hair by the total number of women. So here in this case, I already told you about these numbers, that there are 25 persons who are they are women and they have short hair and they have long hair, and the total woman is 50. So just put these numbers into maths, it comes out to be 50%. And if you talk about the other scenario, which we were considering, the men's restroom. So this time also, we have, I told you earlier that there are 2 women only, and one is having the short hair, another is having the long hair, and we are calculating the probability. So this again comes out to be 50%, right? So doing this same thing with the men also. So what is the probability that someone has long hair and you are given that it's a man? This is given. You know that the person is man. What is the probability that the person is having the long hair also? So this comes out to be 2 have long hair only, and total persons are 50. This is the normal scenario which we are considering, and this comes out to be 4%, right? And talking about the other case, when we are considering the men's restroom line, so here also the probability that the people, the long hair and a man, this comes out to be 4%, so it doesn't change. So basically, conditional probability is that if I know that B is the case, then what is the probability that A is also the case? In case of conditional probability, when one thing is true, it's not necessary that the other thing is also true. Let us consider this example. Let us suppose I'm having a puppy, I'm holding a puppy, And I asked you, what is the probability that it's cute? So the probability would be very high, right? If I consider this case, I'm having the puppy and I'm asking you, what is the probability that it is cute? Then the probability would be very high. You will say, yes, it would be cute. And if I consider, if I take it the other way around, and I'm holding something which is cute, but I do not know, and I'm asking you, what is the probability that it's a puppy? So if I'm holding something cute, it could be anything. It could be a baby, it could be a puppy, it could be anything cute, right? So there are a lot of things that can be there. So the probability that it is a puppy, it is very less. So these two things are not interchangeable in case of the conditional probability, right? In case of this, probability of A given B and the probability of B given A, this is not same, right? So this is one important thing which you should keep it in your mind. This is the conditional probability. So let's talk about the another concept of joint probabilities. So this is another concept. If I talk about the joint probability, joint means the two and more things, they are existing together, they are true together. So what's the probability that a person is a woman and has short hair? Both these things have to be true. But in the previous scenario, when we were talking about the conditional probability, it was that we were actually trying to find out the probability of something, some hypothesis, and given one event is true. But here it's a joint probability. We are saying that both these things should be true. So the joint probability, I'm asking here that what is the probability that a person is both a woman and has short hair? So to calculate this joint probability, you first find out their conditional probability. This, you know, this is conditional probability. And then you multiply this by the probability that there are women, right? And so in this first scenario, all the figures are already in front of you. So you will come to know that this comes out to be 0.5% is we calculated, and it is the probability that it's a woman. That was also earlier we calculated as 50%. So this comes out to be 0.25, which is 25%, which is exactly what we know it was going to be. And this is similarly for all the different conditions. Here we calculated the probability for the short hair, and here we are similarly we can calculate the joint probability for the long hair as well, right? And this also comes out to be 25%. Now, if I talk about the other scenario which we are considering in this example for the men's restroom. So here the probability that someone is a man and has long hair. So here also you will use the conditional probability and the probability that it's a man. And what is the probability that the person has long hair and the man, and it's a man, this is given to you. So from here, from all these figures that we are having, you calculate that this comes out to be 4%. Right? And now I told you that conditional probability A given B or B given A, they are not interchangeable. But in case of the joint probabilities, they are different than the conditional probabilities. Here the probability that A and the probability that A and B, this is the case, this is same as the probability that B and A is the case. So they are same. There is no change in it. So both can be calculated, both are equal. So We can take one example for this. If you have something like that, that you can see on the picture, that if I say that what is the probability that I am having a jelly donut with my milk, this is same as the probability that I'm having milk with my jelly donuts. So both these conditions, they are identical, so we can swap the order, it doesn't matter. Both these probabilities, they can be same, but in case of conditional probabilities, they were different. Now we are talking about the last concept, that is the marginal probability. So here, if I wanted to figure out the probability that someone has long hair, right? So what I'm going to do is I want to just find out what is the probability that someone has long hair. So it could be a man with the long hair, it could be a woman with the long hair. So what I'm going to do is I just add up all the different ways if someone can have long hair. They can be a woman with the long hair, or it can be a man with the long hair, and all these figures we are already having. So this is 1% probability and 4% probability, and it comes out to be 5% probability. So overall, you can do the same thing for the short hair as well. What is the marginal probability that someone has short hair? So you will consider all the cases, woman with short hair and man with short hair, and this comes out to be 95%. So now this finishes our foundation for the Bayesian theorem. So we can get to what we really care about, is that this person has a long hair. So what is this we wanted to calculate, what is the probability that it's a man or it's a woman? We do not have this answer, although we have calculated a number of probabilities, but we still are not with this answer that what is the probability that someone with the long hair is a man or it's a woman? What is the probability? So here comes the Thomas Bayes theorem. So he noticed something really cool, that you can calculate the joint probability that someone is a man and has long hair, right? And using this formula that we just saw before, right? And you can also calculate the joint probability that someone has long hair and it is a man. Now, these are the different formulas that we just remember, that the joint probabilities, they don't care about the order, right? So these are the joint probabilities. Someone is a man with long hair and someone is someone with the long hair is a man. So these are the joint probabilities. So, and I told you that the joint probability, the order doesn't matter. So these two are same, whether it is written man first and the long hair second, long hair first and the man second. So both are same. So if the left hand sides are same, then the right hand sides are also equal. So we are equating the right hand sides also. How we are calculating the man with the long hair and long hair, and it's a man. So these two are equated, and this is how we are calculating the long hair we have, right? The second term is with you, that is the event, and you want to find out what is the probability that it's a man. This is what you want to find out. So that was not a straightforward way to calculate this. We had to calculate the joint probabilities, the marginal probabilities, and the conditional probabilities, right? So this is how this equation has come out to you, and this is called the Bayes theorem. And if we just replace these values and we just generalize these terms, the man with some event A and the long hair with some event B, So, and if we are putting all these numbers together, so this gives you the formula for the Bayes theorem, right? It was not just straight way that we can find out that what is the probability if something is given to you. It depends upon lot many other factors. You have to calculate the different probabilities. So this is the formula that we have just derived from this entire example, that how we can come up with this probability, that if you want to calculate what is the probability someone is a man, and the long hair information you have, just with one piece of information that the person is having the long hair, you want to find out that whether it's a man or it's a woman. And depending upon the scenario that you were considering, whether that person was just a part of the theater or whether that person was standing in the men's restroom line, so the things and the probabilities would different, right? So this we have calculated the generalized formula for the Bayes theorem from this particular example. I hope you people understood that how we came up with this Bayes theorem from that example. That was a very simple and a easy way to understand this Bayes theorem. So now let's just calculate the probability that the person is a man. If the person is having the long hair, we are just putting in all the values, all the numbers. I told you how to calculate this also. Here you will consider this is the marginal probability, this is the conditional probability, and this is the normal probability, right? So you're putting in all these values. You have calculated all these things earlier during the example when we were considering the normal scenario. So this comes out to be 7%. There are 7% is the probability that the person with the long hair is the man. And if we talk about the another scenario that we were talking about the men's restroom, here the probability is different. So here the probability comes out to be, if you are putting all these numbers from this example, it comes out to be 80%. So this really makes sense. It's so now we can say that Bayes theorem is quite helpful in letting us know that depending upon the scenarios, depending upon the information you have, how you can make an intelligent guess. It's nothing but a kind of guess that you have made, but based upon some mathematics. So Bayes theorem is nothing. This is the mathematics plus the guessing work, right? So here 80% are the chances that if the person is standing in the men's restroom line and the person has a long hair, then 80% chances are there that it's a man. And if we talk about the another scenario, then only 7% is the probability that the person with the long hair is a man. So it's really making sense. So that means Bayes theorem is quite helpful in letting us know that how we can calculate the probabilities and the chances of making some hypothesis and given the event is true, right? So Bayesian theorem, it's we are not always aware of what we believe. Generally, what happens is, some people keep on believing. The hardest part of this Bayesian theorem is to calculate the hypothesis that P of X. I told you this is the hardest part of this Bayesian theorem, where some prior information you should have. In some of the cases, some people consider this as the 100%. In case of the missing of the instance, when there is nothing prior, when you are just beginning with some event, there is nothing prior, right? So it entirely depends upon you that what you consider this P of H. It could be 100%. For some people, it could be 0% for some people, depending upon how you make the guesses, what you are assuming in that particular situation. So this is how the selection of the pH matters. But once you have got some evidence, you have some values at hand of first experiment, so that becomes the prior for the second experiment. And then with the lot many experiments, you keep on improving, and the probabilities they keep on improving, and you're quite close to the exact guesses or the probabilities. So this is how this Bayes theorem works. I hope you people understood this concept of Bayes theorem. And now if I talk about some real-time applications of Bayes theorem. So this is now being used in lot many real world applications. If we just talk about the medicines. So in the medicines, what happens is in the medicine line, this Bayes theorem is being used to make some guesses for the diagnosis of the disease. We make the probabilities based upon the results we have of the patients, and then the doctors use this Bayesian theorem to advise the diagnose the disease, and then to advise the treatment for the patients, right? So this is being used in the healthcare sector as well. And another important application is the document classification. So this is quite okay. You must be familiar with this earlier also, that the classification of the documents can be done with the help of this Bayesian classification. Then in the information retrieval and for the semantic searches also, this Bayesian theorem is being used. And you are also, you may be aware about this spam filters, and spam filters, they also use this Bayesian filters, which, make the classification based upon the words, whether that particular word in your email that belongs to the genuine class or that belongs to the spam category. So based upon that, this Bayesian filter, it gives you some very good results. Then this is also being used in the turbo code. This turbo code is being used in the 3G and the 4G networks, and here this Bayesian classification is quite helpful in the turbo code. So this was all about the Bayesian inference and the Bayesian classification that I wanted to share with you. There is one a more important concept in machine learning that we all use a lot many times, but I have seen that the students and even the faculty, they get confused with certain things, and they are not clear with this idea that at which particular situation which performance metrics we need to use. So I wanted to share this another concept with you through this platform, so that you people, because you will be working with the machine learning algorithms, and you will be evaluating your models based upon the metrics. So this would really help you in coming up with the idea that at what in which situation you should use which metric, and which is the best metric to decide that this algorithm is working well in this particular situation. So it's not always that accuracy is just the metric that you should always rely on. Depending upon the situation, depending upon the problem that you are having at hand, you should decide that whether you should go with the recall or the precision or the F1 score. So these are the various performance metrics. So I wanted to talk about this also. So let's just start with my another discussion. So we know that different performance metrics are used to evaluate different machine learning algorithms, and the metrics that you choose to evaluate your machine learning model is very important, right? And the choice of metrics that influences how the performance of the machine learning algorithm is measured and compared. So the first metric is the confusion matrix that you all have been using. And confusion matrix is one of the most intuitive and the easiest. And easiest, but it's not the easiest. This is very confusing. So this is a very intuitive metric which is used for finding the correctness and the accuracy of the model. And it is used for the classification problem where the output can be of one or more types of classes. So let's just take one more example over here to understand the different matrix and the situations. So let us consider that you are solving a classification problem where we are predicting whether a person is suffering from a rare disease, let us say cancer, or no. So we are predicting here, we are classifying that whether a person is suffering, is having cancer or no. So just remember this thing. This is the example that we are going to talk in the understanding of this evaluation matrix. So let's just give a label to the target variable. And here, when the person is having a disease, we'll say it 1. And when the person is not having a disease, not having cancer, we are tagging it as a 0. We are labeling it as 0. So now we have identified the problem. So confusion matrix is what? It's nothing, but it's a table with 2 dimensions, right? Now where we have the actual and the predicted values and the set of classes in both these dimensions. So actual classification, these are the columns, right? Actual classified, this is actually classified as having the cancer, and this is actually classified into the category with the person having not cancer. And predicted is the one which is in the rows, right? Here all the predictions which belong to, here we are making the prediction that the person is suffering from cancer, and here we have the predictions when the person is not suffering from cancer, right? Now, there are some terms which you are seeing in this matrix. First is the true positive. So what is true positive? True positive are the cases when the actual class of the data, this is the actual class of the data, which is 1, and the predicted class of the data. This is also true. When both these things are true, we are saying that this is true positive, right? True negative, this is also very easy. These are the cases when the actual class of the data is 0 and the predicted is also 0. Predicted is 0 and the actual class is also 0, right? For example, here we are having the persons who are actually having the cancer. Actually, they are suffering from cancer, and the model is also classifying them as having the cancer. That's okay. So in the true negative, we have the people, we have the persons who are not having the cancer. They are not having the cancer actually. And our model is also not predicting them as having the cancer. So that's okay. Model is also saying the same thing. And actually, they are also not suffering from cancer. Now let's talk about the false positive. So what is this false positive? These are the cases when the actual class of the data was false. Actually, it is false, but it is predicted as 1. False is because the model has predicted. Why this is called false? When there is a difference in the prediction of the model and the actual values, then you put false, then you call it false, right? So false is because the model has predicted incorrectly. And why this is called positive? Positive because the class predicted was a positive one. This is predicted as positive. So that is why this is called positive, right? And here we'll have the person who is having the cancer. The person is a person having the cancer, and the model classifying his case as the cancer comes under the false positive. The person is not having the cancer, right? Actually, the person is not having the cancer, but your model is saying that the person is suffering from cancer. False positive, right? Then we have false negative. Why false? Because there is a difference in the prediction of the model and the actual value. So you will put the call it false. And why this is negative? Negative because the class predicted, here the class which is predicted is the negative one. So here we'll have the person who is having the cancer. Actually, the person is having cancer and the model is classifying him as not having cancer. The model is saying the person is not having cancer, but actually that person is having cancer. This is a really difficult situation, right? This is a very dangerous situation. So the ideal scenario is that we want that our model should give 0 false positive. This value, ideally we want that this value should be 0 and your false negative value should also be 0, right? But that's not the case in the real life, as any model cannot be 100% accurate most of the time. So this ideal case doesn't happen. We know that there will be some errors which are associated with every model and that we use for predicting the true class of the target variable. So this will result in these false positives and the false negatives, right? And there is actually no hard rule that says that what should be minimized in all situations. It purely depends upon the problem that you are having and the context of the problem that you're trying to solve. So let's just see that when we should minimize what. The first thing is, if we want to minimize the false negative, let's say in our cancer detection problem example, out of the 100 people, let's say out of the 100 people, only 5 people have cancer, right? Only 5 people are actually suffering from cancer. So in this case, we want to correctly classify all the cancerous patients as even a very, we want that even if we are selecting a very bad model, even it should predict everyone who is having the cancer, that person should be detected. So that will give you 95% accuracy, right? If you talk about accuracy. But in order to capture all the cancer cases, we might end up making a classification when the person actually not having a cancer is classified as a cancer. This might be okay as it is less dangerous than not identifying. If someone is not suffering from cancer, but you say that, oh, the person is suffering, your model is depicting that, predicting that the person is suffering from cancer, that's okay. Because we can go for more tests which can make it certain that whether the person which your model is predicting is actually suffering from cancer or no. But the other scenario is quite dangerous when your model is not predicting the person who is actually suffering from cancer. Your model is not considering, and your model is saying that this person who is actually suffering from cancer, and your model is saying no, you're not suffering from cancer. So that person is really at the stake of the health, right? So stake of life. So that's a bad situation. But missing any cancer patient, it's a huge mistake, and because no further examination will be done on that. So this is one scenario. Another is minimizing the false positives. So let's take one more example to understand this. Now suppose your model is classifying the email. Your email is a spam or no, right? So it's a spam or it's a non-spam. So let's say that you are expecting an important email, right? Like some important email you are expecting, and suppose that the email is a spam, then you are giving it the value 1, and if it is non-spam, then you are saying it is 0. Suppose the model classifies that important email that you are desperately waiting for as spam. So this is the case of false positive. This is the case of your false positive. Important email that you are waiting, but your model is saying that it's a spam. So now in this situation, this is also a bad thing. Then classifying an email as a spam email as important, or not spam, since in that case we can still go ahead and manually delete it, and it's not a pain if it happens once in a while. So in case of the spam email classification, missing the false positive is more important than false negatives. So it depends upon entirely on the situation that you are working with, whether you are working with the crucial data, whether you are working with the data where you can handle some discrepancies. So it depends upon you that which measure you want to go with. Then we know this accuracy. Accuracy is another metric in the classification problems. So this is the number of the correct predictions made by the model divided by all other kind of predictions which are made. So this is how it is calculated. Now, another question is that when we should use accuracy and when we should not use accuracy. Accuracy is actually a good measure when the target variable classes in the data are nearly balanced. When you have the balanced data, you have almost equal number of samples in both the classes that you are having, then at that time you can go with the accuracy. And but when you are having unbalanced data, when you are having one class is having many data samples and then other classes having very less data, then in that particular scenario, accuracy should never be used as for determining or for evaluating your model. You should never use this accuracy. For example, just take the case of the cancer detection example only. Suppose there are 100 people and 5 people, there are 100 people, 5 people are suffering from cancer, right? Let's say that our model is very bad and it predicts every case as no cancer. Your model is saying there is no cancer. So these are the people who are actually suffering from cancer, but your model is not able to predict them. And your model is saying there is no cancer patient. So in doing so, it has classified those 95% non-cancer patients correctly. But 5 cancer patients, they have also been predicted as non-cancerous. Now, even though the model is bad in predicting the cancer, the accuracy of this model will come out to be 95%. So you will say that my model is very bad, is very good, because the accuracy of the model is 95%. This is pretty good accuracy. So I should select this model. But actually, if you just see at this particular scenario, your model has not considered this important scenario. Your model has skipped those patients who were actually suffering from cancer. So that in that sense, this accuracy is not a good measure to evaluate your model. If you're working with the crucial data and when you are actually having the unbalanced data, accuracy should never be used. Then there is another metric, precision. This is an important metric. Precision is a measure that tells us what proportion of patients that we diagnosed as having cancer actually had cancer. This is really important. It tells us that the patients that we are diagnosing having cancer and they actually had the cancer. So the predicted positive, the people predicted as cancerous are PP and FP, right? So these are the people who are predicted as positive cases by your model, because here we are in the rows, we are having the predictions. So in this our cancer example with 100 people and 5 people are actually suffering from cancer. So let's say our model is again very bad and it predicts every case as cancer. So since we are predicting everyone as having cancer, then your denominator, this would be 100, and the numerator, the person having the cancer and the model which is predicting his case, it would be 5. So the precision in this particular case comes out to be 5, because precision is nothing but this is TP over TP plus FP, right? So this is your 5 by 100. So this comes out to be 5%. So the model's precision is 5%. Let's just move on to the next metric, that is recall. So recall is a measure that tells us that what proportion of patients that actually have cancer and it was diagnosed by the algorithm as having cancer. So the actual positives, the people having the cancer, they are TP and FN. So these are the people who are actually having the cancer. So TP plus FN, right? And this recall is calculated as TP over TP plus FN. Right? So here FN is included because a person actually had a cancer, even though the model predicted otherwise, right? Actually, it is having the cancer, but your model is not predicting that person. So in this example, our model is predicting every case as a cancer. So here in this case, the recall in this particular example, this comes out to be 100%. Now you have got these two metrics, recall and precision. Now when to use precision and when to use recall? So this is important. So it is clear that the recall gives us the information about the performance of the classifier with respect to the false negatives as well, right? How many we missed. So while precision, it gives us the information about its performance with respect to the false positives, that how many we caught, how many are predicted, and here it tells us that how many we missed actually. So precision, as the name says, it is about being precise, how precise your model is. So even if we manage to capture only one cancer case and we captured it correctly, then we can say that we are 100% precise. But recall is not much about capturing the cases correctly, but it is more about capturing all the cases that have cancer with the answer as cancer. All the ones who are actually suffering from cancer, and it is also saying them as cancer. So if we always say that every case as a cancer, and we would say that the recall to be as close as 100% possible, and so then in that case we would want to minimize, we would focus on minimizing the false positives, right? And and if we want the other case, then we would focus should be onto making the precision as close as 100% possible. Then we should try to minimize the false positives in that case. Then apart from this recall and precision, there is another important metric which is called F1 score. This is nothing but this is the harmonic mean between precision and recall, right? And generally in most of the cases we use this F1 measure, and because this considers both the recall and the precision into consideration, and precision and recall are very important metrics rather than just relying on the accuracy. Accuracy is not always the best measure that you should just consider, and when to use recall and when to go with the precision, this depends upon the situation that you are having. So that's all for today from my side. So if you have any queries, you can ask me. Thank you so much, everyone. Yeah. Thank you so much, everyone. I hope I made myself understood to you about the concepts, about the Bayesian, how we derived and how we reached to the formula of the Bayesian inference. And then the another concept that I really wanted to share, because I can just see that most of the students are sitting over here, and they must be using this machine learning in all the projects, and nowadays this is being used. So the performance metrics, this is again very important, which is a part of every machine learning algorithm. And I hope you understood that in which situation we should go with the different performance metrics. So if you have any queries, any doubts, you can ask me. If sir is speaking, sir is not audible to me.
I'm audible, ma'am?
Yes, yes, sir. Now you're audible.
Okay, thanks a lot, ma'am. Any question from your participants?
Sir, ma'am, it was a very good presentation. I just want to know about the confusion matrix if the classification problem is not 0-1 based, if it has more than 1-2 classifier.
Yes.
So what will be the confusion matrix in that particular case?
So, you know, even I was going through this, that nowadays it's not just 2x2 matrix that we talk about. There, it's more than that. It's, you know, it's not just 2x2. It could be 3x3. It could be 5x5. Then there are a lot many other new matrix that have been introduced besides this, you know, false positive, false negative, and this. Precision and recall. So I was just going through that also, that nowadays it's not just 2x2 matrix, it's 3x3, it could be 5x5, it could be of more dimensions. And whenever we talk about the multi-class classification, then what we do is we first of all we try to classify into 2 categories, and then once it has been done, then we consider that as 1 category, and then we try to categorize and classify the 3rd category also. So there are lot many things, there are lot many algorithms which are available for doing this multi-class classification. And there are some algorithms which do just binary classification. So you should go with that which particular algorithm you are using, whether it's a multi-class classification or this is the binary classification. You're not audible.
I'm very sorry. Even multi-class classification actually uses binary classification, as you also pointed out. So the thing is, we should create confusion matrix for each and every binary classification, or there'll be a proper, I don't know, 4 to 5, 4 cross.
So it has to be. Matrix. It could be done that way also, because nowadays it's not just it's not just the binary that I told you. It's not just 2x2 dimension, as I just showed you in my PPT, because that's the basic one to have the foundation for the understanding. But nowadays it's much more than that, and there are a lot many new metrics have also been introduced. So what you can do is, if you want to go with this, so you can first of all just try to focus on 2 classes, and you can have that 2x2 binary classification, and then stepwise you just move on to the next classification problem. So this is how it could be done.
About accuracy, precision, the formula which you have told will not change, certainly, I guess. Because
if you would do it in a stepwise, then it's not going to change. It's going to be the
if I'll consider everything in one go, then probably it will change.
Yes, you cannot do so, because if you're having the multiple classes, then you cannot do so. You have to go step by step, right?
Yeah.
You know, if I just, I would like to share one more thing with you people. When I was doing my PhD, in that my doctorate degree, I was working on the spam classification on Twitter. So what I did was I classified the spammers. First of all, I was classifying whether this person is a genuine person or it's a spammer, right? And then further, my another purpose was to further classify the spammers into different categories, whether that person belongs to the fake profile, whether it's a fake profile, whether it's a compromised account, whether it's a sole spammer, whether this person is a pornographic user, whether that person belongs to the another category, which we call it as the merchants, the following merchants, they are called, the ones who are engaged in, you know, increasing the followers. So they are also a kind of spammers who are, you know, distributing spam in the network by their illegal activities. So this was my problem. I had to classify this into different classifications. So I was looking for this multi-class, as you just mentioned, for the multiple classification. So I was really not able to do this at that time. And so I did that binary classification first. First, I classified that whether this particular person is a spam or it's a genuine user. Then once I got the information about the spam users, then what I did is I designed one algorithm which was classifying based upon their features, that whether this person belongs to a fake user, whether this is a compromised account, and there are 5 different categories on which that classification has been done. So this is how I took up this particular situation and this particular scenario. So
thank you, ma'am. It was enlightening session. If anyone
thank you
has
so
any
much.
question,
Yeah, so the students,
students.
yeah,
so I'm
okay,
expecting they ask some questions, like at least those who have studied machine learning, because I
yes,
teach them.
Okay, so you these are your ME students or BE students?
Not BTech, and some of them are BTech
BTech.
first year and BTech second year. I'm not very certain
Okay.
about online.
All right, yes,
So
because
from online, if anyone wants to ask, you can unmute yourself and you can ask, or you can just drop a question as a text message also. That will be also okay. Please go ahead. Bhajan, please.
Monica ma'am, I have a wonderful question.
Yes, sir.
We have been, you know, facing COVID for the last 2 years.
Yes.
Initially, we got an RT-PCR kit.
Yes.
And the rate of testing, I think the efficiency was just at 50%. Yes. Since it has been imported from China.
Yes.
Right. And after 1 year, I think it's been considerably improved in testing. And now we have the real-time RT-PCR testing.
Yes.
So what is the, you know, the logic and the machine learning algorithm been incorporated in that RT-PCR kit? Any idea?
Basically, any machine learning algorithm or any this prediction algorithm, it takes the data set into consideration. So whatever data we have, so it is trained on that, on the number of samples, right? And it must be taking some features which are able to predict that this particular person is suffering from COVID or no. So those features and the models, they are being trained on the data. So as more and more data, you know, keeps on accumulating, the performance becomes better. As you mentioned that earlier, they were not accurate because the data set was less. But as more and more training happened, because machine learning is all about training your data. So more you will train your data, the better would be the performance of the model. So now, since it's been 2 years and there is a lot of data we have at different labs, so the accuracy of the kits has also been improved. So we can rely on those kits. This is how this machine learning actually works.
Second question is about the vaccine formulation.
What's the
Vaccine.
Okay, right.
Co-vaccine
Okay, yes,
formulation.
yes.
The thing is, initially we have very less number of that volunteers for the vaccine.
Yes, right.
And the phase 1, the phase 2, and the phase 3, and even the Indian, the Covaxin, they have infused the vaccine by even not going the phase 3.
Yes.
And so don't you think that we are using so many concepts of the machine learning algorithm or any techniques, and it is a case of the typically healthcare?
Yes.
And it's not if a machine fails and we can recover, it's in concern with the lives of the people.
Yes.
So don't you think that it's very, very ethical and to use the machine learning concept or the AI concept?
Well, sir, this is really very nice question. And, I was delivering a talk. I was giving a lecture to someone in some other FDP, and that was related to 5G. And where we were talking that how this 5G networks, they can be used in the healthcare sector. So there I was giving an example of the situation where the remote healthcare that is being done. So what is happening is nowadays, if you just see that everything is remotely being done. Even the doctors, they do not actually go to the patient and do the operation. So this is what is happening in the healthcare sector, and this is all health sector, we can say. And if we just talk about these cases, so these things are becoming so precise, and even the patients and even the doctors, they are relying on this, and there are the robots who are actually doing the operation. And there are a lot many other examples where this healthcare sector and this medicine field, this is relying on this machine learning algorithms, because they are actually giving them the precise results. The doctors are using machine learning algorithms for predicting the disease, depending upon the symptoms, depending upon the data they have about the patient. So they just predict the disease, and if they're not sure, they can go for the more tests which can make the prediction better. So this machine learning is actually being used in every important sector, and we are talking about the healthcare sector, which is very crucial, right? And we cannot do anything wrong at the stake of the life of any person. But we are relying on machine learning because they are very much precise. They are much precise than the human beings, because even the human beings can go wrong, but machine once learn something, it can never go, it can not go wrong, right? So this is why this healthcare sector is relying so much on this machine learning, that it is being introduced everywhere, whether this is, the operations are being done remotely, or we are nowadays, we have been talking to the doctors on the video calls. We are telling them these are the symptoms, this is what is happening to us, so suggest something. So this is all, they are keep on updating their database, and then it is also helping making the predictions of the doctor and diagnosing the patients better with the help of the data, and by using these machine learning algorithms. And this is what I want to say on this.
Good afternoon, ma'am.
Good afternoon, dear. How are you?
Fine, ma'am.
So after a long time in the campus?
Yes, ma'am.
Okay.
Ma'am, I have a question. You said performance matrices are used for testing a model, a machine learning model. Is there any other way of testing the model other than the confusion matrix? Are there any other?
Confusion matrix, actually all other metrics that we use for evaluating the performance of the model, they all are basically one way or the other, they are related with the confusion matrix. Whether you rely on the specificity, whether you rely on the sensitivity, the recall, precision, accuracy, and F1 score, they all actually came some way or the other from the confusion matrix. So it's actually confusion matrix is not the metric, but it's just the foundation for all these metrics which help you to evaluate the performance of the model. So yes.
Then we can say that it's the basic.
Yes. This is the foundation from which will tell you that how many predictions are actually true and your model is predicting them so. So this is all these metrics, they are basically related to the confusion matrix only.
Okay, thank you, ma'am.
Thank you, dear. All the best.
Thank you, ma'am. Anyone else has any questions? Anyone? No?
So thanks a lot, Monica ma'am.
Thank you, sir.
Have literally enlightened, and it's very, very crucial to discuss, especially the healthcare domain.
Yes.
And everybody is, they are giving their input for the, developing new algorithms, new innovation about your deep learning and IoT concept.
Yes.
Just to have a better life, and we get the better product in terms of its use. So thanks a lot. Yeah, we're just winding up this session, and thanks a lot, ma'am.
Thank you, sir. Thank you so much. Thank you, everyone. So I'm leaving, sir, right?
Yeah, thank you, ma'am.
Yeah, thank you so much.
So we are going to end the meeting. I will meet at tomorrow at 11 a.m. right? Tomorrow at 11 a.m. So thank you for participating.